question about final exam. Is the final exam comprehensive or?
It's comprehensive, that's right. Maybe some motivation to go back. Otherwise, I'm pretty sure you're going to forget about it. So yeah, it's going to be comprehensive. But the emphasis will what we have covered after. Yeah. So I guess when I see the emphasis means the majority of the problems will come from what we covered after. But we do have problems coming from before. So you have to review all the course materials that we have. And by the way, I didn't look up the date, but the final exam will be based on the university schedule. If you go on the UK website, you just type final exam schedule. You can look it up based on the class time. Okay, you can look it up.
I think it's on May 7th.
May 7th. Okay. So you can. I think that is. I don't know. Probably the case for most classes. You can look it up on the website. You go to the school website to find out the schedule. I think most undergraduate classes go by the university schedule. That's my understanding. We are going to finish mutation testing today, and we're going to start a new topic called test data generation. I guess if you look back, we talk about graph-based testing. Like we discussed how you can select test path, right? But we didn't tell you how you can generate test data. And that's what this topic is about. Any other questions before we go on? And I believe we have one more homework. Okay. After homework 7, we have 8 homework assignments, and then that's it. And I know you're going to miss the homework assignments. If you do, try to spend more time on the project. That's the idea we give you. Because we are getting close to the end of the semester. I hope you are going to have more time on the project. What is the motivation for mutation testing? Anyone? Recall? Yeah. Very good. So one way to look at this is basically a systematic approach to add bugs into a program, so that we could do evaluate the effectiveness of testing. And at least this is what we discussed for program-based application testing, and that is the most common application of application testing. And also recall the basic idea of mutation testing is that each time we make a minor change to create a mutant, and that minor change basically mimic like a mistake, a small mistake that you could have made as a program. So that's the basic idea. Finished that. So we finished this slide. Okay. So I just want to mention that if you look at this process, mutation testing is kind of used as a coverage criteria. Okay, if you kill a certain number of mutants, then we stop. So that's the basic idea. The test generation, like this box, okay, you can use like random testing. Okay, you randomly generate test cases, but how many test cases would be adequate, right? Then you use the random tests to see how many mutants. So from a certain perspective, mutation testing in this process is used as a coverage to determine adequacy of test cases. So what we're going to see next is basically some mutation operators. Okay, how you're going to create mutants using the mutation operators. The idea is actually very, very simple. Okay, so if you look at this example, see that's the program, the original program from which you want to create mutants. So what you do is that you can replace like every variable here, okay, with this expression, which is basically to take the absolute value of this variable. This variable could be positive, negative, and you're going to also replace it with minus absolute value, because you can definitely get a negative value. You're going to replace this with like 3 upon 0. Okay, so each one is going to create a mutant. Okay. So it's called absolute value insertion. And this one, arithmetic operator replacement. Very simple idea. Okay. The original program, you have the plus operator, you replace it with minus, you replace it with multiplication, you replace it with division. Why you want to do that? It's because you are trying to mimic the possible mistake the programmer could make, right? You are supposed to put plus. Maybe you have a misunderstanding about the semantics, about what kind of computations you are supposed to do. You may put minus by mistake, or you will just alter your mind, right? Just sometimes when you come back, look at the mistakes, you just couldn't explain why you did what you did. Okay. So very simple idea. Like for every arithmetic operator, you replace that with another arithmetic operator. So that's what we mean by a mutation operator. Okay. Similarly, relational operator replace one relational operator with another relational operator. Okay. Conditional operator replacement. I hope you get the ideas. Very simple ideas. But if you think about the motivation for mutation testing, the problem you have, I mean, we cannot find a better approach to evaluate. Okay, you are evaluating the effectiveness of the okay. So here we have quite some mutation operators. Okay, I hope. I mean, they are all. They all have similar ideas, and I just want to. I don't want to go into the details of each operator. I think it's pretty similar idea. I just want to mention, if you want to apply mutation testing, what kind of challenge can you anticipate? Like if you have to do mutation testing,
There'll be a lot of cases.
there's going to be a lot of mutants that you have to generate. So the idea is that for each mutation operator, you're going to apply it to everywhere in your program. that the mutation operator can be applied.
And only one at a time, right?
One at a time. Each time you're going to create a new program that is slightly different from the original. So that is indeed the biggest challenge of mutation testing. That is why I mentioned before that it's definitely not widely used in practice. Okay, it's mainly used in the research community. And I do want to mention that the research community is making a lot of efforts trying to improve this. For example, some mutants may be equivalent, okay, so that you don't have to test like everyone, right? For each equivalence group, just like equivalence partitioning technique, you only need to test one, right? So that you can reduce the number of mutants. And there are also ideas like prioritize, right? Say you want to spend your effort on those most important ones, of course you have to somehow determine, right, what mutants are more important. There are techniques to do that. And there are tools that are available. Okay, we have our group, because we do so fantastic research, and we have to use mutation testing. So there are different tools that we could use can automatically generate mutants. Okay, like some tool called MuJava, MU Java. This is a mutation tool for Java. I guess one of the most widely used mutation testing tool called PI. You can look it up on the internet, and it's open source, and you can try it. So next, we're going to talk about input space mutation testing. So it's not, so you do not change the program, you change the inputs, okay, that you are going to create in the program. Again, the idea, we're going to just give you some main idea. The details of input space based mutation are not required in this class, because it's still relative. It's still under development, has not been widely used yet. And the main idea is that basically for when you test the program, not only test positive test cases, you also need to test negative test cases. And one reason I want to mention this is because security testing. Okay, security testing, we are going to have to spend more time on that. It's basically negative test. You're going to test invalid or unexpected. And the idea is that you will take the input grammar, okay, so that you can systematically generate invalid ones, and then you test the program with those invalid ones. So let's look at example. Okay. So let's say if you have a application, okay, let's say a banking application that provides a command line interface so that you can type like the command, say deposit, okay, make a deposit. So you make a deposit a certain amount to a given account. And you may say, well, now you guys use graphical user interface, right? You don't necessarily use command line. But remember, in many systems design, you have front end, you have back end, and the back end basically takes like sometimes the front end just take the user inputs and package it to a command and send it to the back end. So in this case, you can say, well, if you want to have a valid input, then you have to have a deposit, which is a keyword, right? This is the command execute, and you have to provide the account number and a certain amount. So what we can do, we try to generate, okay, invalid inputs. We can mutate the grammar. This is the production rule that defines like what kind of commands would be valid. So you're going to replace every non-terminal symbol with a different one. Okay. So in this particular example, account amount, they are non-terminal symbols. Okay, they are not like they can be rewritten. Remember the definition. Deposit would be a terminal symbol. Okay, because you cannot rewrite this one. Okay. So you can replace account with amount. You can replace amount with account. Okay. Then you replace each non-terminal symbol with a different non-terminal symbol, and then you get kind of a mutated grammar. Then you derive strings from the mutated grammar. You know, because the grammar is mutated, so any string that is derived from this grammar is invalid. Okay, this is some kind of input that is not expected. Okay, by the system designer. So like in this case, the case when you say the command like this, you say how the system respond. Okay, and you can put two or three numbers over there. So just get the main idea. Okay, so it's one way for you to generate invalid inputs in a systematic way to test your system. And you can also do terminal replacement. Right? For every terminal symbol, you replace it with another terminal symbol. Okay. And you could do deletion. Okay, so you could delete a terminal symbol or non-terminal symbol from the grammar. And you get the mutated grammar, and from which you could generate values. And I just want to mention that later you will say that I don't know if you guys heard about SQL attack. SQL injection attack. Like in some places you are not supposed to have a special character. If you put a special character over here and you compromise. We're going to discuss more when we talk about security testing. But those kind of inputs, okay, could be derived from just one possible application of this. And if you can do duplication, right? The same symbol you're going to put it twice. Okay, so that's another way to generate invalid elements in the systematic. I want to mention that. See, later we will discuss negative testing can be more challenging than positive testing. Because in general, the negative space is much bigger than the positive space. And also for the positive space, you kind of know more about the structure so that you can kind of like navigate the structure to select the representatives, right? That's basically what testing is about. The negative space is so huge, right? And we do not know much about it. And that becomes very difficult for you to be systematic to generate representatives from the negative space. So from a certain perspective, like if you mutate the grammar structure, it's kind of a way to navigate the negative, the structure of the negative space, so that you can be more systematic when you try to select representatives. Okay, so, but this is still kind of like very research active topic. I guess the main challenge is that we can generate a lot of it. Okay, and that's the general challenge with negatives. Okay, the negative space is just so huge. How can you select that without knowing much about the structure of the negative space? How you select representatives, right? But this is one possible idea to approach that. So to summarize, mutation testing is a kind of syntax-based testing. It tries to generate mutants or tests, okay, for the syntactic structure of the subject we're trying to test. And remember, program mutation operators are defined to mimic program mistakes or for certain types of tests you generate, like the ARM statement. So it just forces at least one test generated to reach that point. So that's for the second case. And input space mutation operators are defined to generate embodied tests. Relatively speaking, program mutation testing is more mature, mainly in the research community, has been widely used in the research community. That is very interesting. But input space mutation testing is a very new idea as it's still under active development. That's what we have for mutation testing. I just want to mention that we don't have to get into the details of mutation testing. What we need to understand is what we discussed in the class. If you want to kill the mutant, what conditions have to be satisfied? There's three conditions: visibility condition, infection, right, and propagation. And that's also what the whole assignment is about. That is the main thing that we want to understand and the general. All right. Any questions about mutation testing before we move on to test data generations? So, first of all, I want to make it familiar. This is again a very research active topic. If you read the textbook and not separate, I don't think the textbook actually covers this topic. Okay. So as you know, right? The reason why it is not covered, as you can see, it's a very important topic, right? Because in the end, you have to generate the test cases. The test part that we, for example, we select by itself cannot be executed, right? You have to generate test data. But the textbook does not cover. It's both textbooks. Okay, I have the foundation software testing as the first reference book. Does not cover this topic. The reason is because it is not mature. Or another way to put it, it is an advanced topic. Okay. Yeah.
Is testing in general still kind of new to the research community?
Yeah, relatively speaking, actually, software testing this class is not offered until very recent. And many schools, even now, many schools, like they do not have software testing. So that is definitely true.
So I think like even like, you know, if you just Google, like our book's title is just this form straight introduction to software testing.
Right.
And it's pretty much the only thing that shows up.
That's
when you-
right.
when you
Yeah,
put it
that's
in.
right.
It's
Yeah.
not-
Right,
like-
indeed. I believe this textbook is the most widely used textbook for software testing class. I forgot who did that. We actually did a survey. We had a website like listed all the software testing classes that are.
Yeah, I have done that.
Oh, you did that.
And
also the
the
textbook.
website. Right?
Yeah, the website. I think that website is still up somewhere. Right? That was a
Yeah,
couple of years ago.
Yeah, it's I think it's 2030.
2013.
Okay.
Yeah. Yeah. Now I think we have more classes. Most schools are teaching software testing, but relatively speaking, it is a new area, new topic. Okay. So we have a so again for this topic, we're not going to have a homework assignment. Okay. I just want to give you the general idea. I think it's an interesting topic to talk about. It's something good to know, and it,
Probably be useful for
yeah.
the project.
right. Yeah, you can definitely you could probably apply some general ideas to the project. You probably have to do it manually, okay, instead of having a tool. But the basic idea is the same. The tool is trying to automate what I guess you have to do manually on the project. But this is a very, very active research area. A lot of people working on this. I believe there will be more programs probably very soon, so that at least you could understand what is behind, and maybe someday we're going to have a tool that you could use to automatically generate test data, and you could easily understand what is going on, and that's the purpose of this talk. And also, I want to give you a complete picture, right? If we stop at the testing path, you may be wondering, that's not our destination, right? We still want to have test data. So we have an introduction. We're going to discuss two approaches, okay? Two automatic test data generation, just to get the main idea and the challenges with this problem. So this I consider to be one of the grand challenges of software testing. Okay. So giving one or more test path, okay, here make it simple. Giving one path, okay, program path, the sequence of statements that we want to execute. How to automatically generate data inputs, such that if you give the data inputs to the program is going to execute the path that you want to execute. Very well defined problem, right? So if you look back what we discussed before, like those graph-based testing techniques will generate a set of test paths. So next question is, for each test path, what kind of test inputs you want to produce so that the path can exercise. That's basically the problem. Okay. So before I give you the main idea, let me ask you, okay, now you have a path. Remember, program has branching structure, right? Loop structure. Okay. So if I pick a particular path, okay, you can imagine the control flow graph, right? I pick one particular path from the control flow graph. I want to ask you to automatically generate. But maybe forget about automatically. I want to ask you to generate as the inputs to exercise that path. What you have to do? How you will approach this problem from your perspective? Yeah.
Don't you have to make sure that the inputs that you put are also internal variables too?
You can again, if you are talking about the external variables, for this problem, you can only generate, you can only control external variables, and you can only assign values to external variables. You cannot directly assign values to internal variables. Just to keep this in mind. Sorry, you continue. Yeah, how you going to do it? Are you finished? You're still okay. So I guess your point is that you need to figure out the relationship between external variables and the internal variables, right? That's probably your point. Yeah, that's definitely one challenge. Yeah.
First,
thing I would do, I would look at the limits.
Okay.
Use numbers higher than the limit, or within the limit, or lower than the limit.
What do you mean limit?
If there's a range of a variable less than 4 and more than, then I would.
So that's like equivalence partition we mentioned. But how you could you correspond that with the path that you want to exercise?
First you look for all conditional statements.
You're getting close, yeah. Why you want to do that?
I think that's gonna determine where you branch and how you branch.
Okay, very good. Okay, so from a technical perspective, if you want to force a particular path to be exercised, what you really have to do is that at each branching point, you need to make the right choice. That's basically what you have to do to force a path, a given path to be exercised. So imagine like if you have a control flow graph. So you have a branching structure, I don't know. I'm just giving you an abstract graph, like you have a loop, and then you get out of the loop. Okay. So let's say if I want to execute a particular path, okay. If I want to execute 1, 2, 3, 4, 5, well, that is not possible. 1, 2, 3, 4, 3, 5. If I want to execute this, right? What you really have to do is that you look at the branching point, the statement, the conditional statement, basically, on the path. You want to make sure, like for example, for the first one, you have to make sure if this is true, this is false. You have to make sure the condition is true, so that you can take this branch, right? Otherwise, you're not going to exercise this path, right? Then you continue, you look at the next branching point. In this case, as you can imagine, is a loop statement, okay? And this is also a conditional statement. You want to make sure you're going to execute. This is true, this is false branch, right? Get out of the loop. You have to make sure this condition is true when you come to this point, so that you can take the right branch. So imagine giving a path, you identify all the branching points, right? Because basically they are conditional statements. You want to make sure each branching, at each branching point, you make the right choice. Then you basically force the path that you want to exercise, right? So I guess the point is that it's basically about how you can generate test inputs so that the branching conditions are evaluated to a certain way that you want the condition to be. Okay, that's the basic idea. Okay. So you want to connect all the branching conditions into the path condition. Okay. So if, for example, if this is branching condition C1, this is branching condition C2. If you want to exercise this path, okay, so C1 has to be true, right? And C2 has to be true for the first time. And then for the second time, you can put the superscript, okay? For the second time, when you come to this branching condition, it has to be false. If I use this indicate negation, has to be false. If you can make sure this condition, if you generate, let's say some test inputs, you evaluate them, okay? On this condition, if this condition is true, you know the path is being exercised. It's close, but different because
We're not putting
this
the same
is not
requirements on it, right?
Right. Right. You only need to find one one possible assignment to the external variable so that this condition is true. So this is more like a constraint. Okay. So you have to constraint solve after you have, because as you can imagine, you could have any branching condition. You have to put them together into a path condition, such that if this path condition is satisfied, then the path will be definitely exercised. That's the basic idea. Right, you can have more challenges, right? Again, that goes to the internal variables and external variables. Let me ask you this. Like now I use the superscript, C1 and C2, right? C super 1, C super 2. They are different conditions, right? They are definitely not the same condition. Because if they are the same condition, there's no way for you to satisfy, right? It could be a contradiction, true and not true. What's the difference between these two conditions?
Whatever happens. And then for.
That's right. So basically, you have done some computations, right, inside the loop. So if you imagine like you're going to rewrite, so you could have internal variables, right, involved in these conditions. Okay. So those internal variables will be different. There are some computations have that you have different values. And generally speaking, if we recall what we discussed in the program-based predicate testing, so the branching condition, so they typically are written in terms of internal variables, right? But when we generate test data, the test data has to be in terms of external variables. So if you want to solve this constraint, you have to rewrite. You have to figure out the relationship between every internal variable with the external variable. And as you can imagine at this point, before you execute the loop, the relationship between the internal variable and the external variable will be different from the relationship between internal variable and the external variable after you execute. So that's the difference. You have to rewrite the expressions, as you can imagine, after you rewrite, it's going to be very different between the two conditions. Okay, conditional expressions. So first, we have to connect all the branching conditions, and those branching conditions have to be written in terms of external variables. That is what symbolic execution is going to do. Not only connect the branching conditions, you have to rewrite. That's difficult, right? When we talk about rewrite, there's a mission. You basically have to figure out the semantics of all the computations you have performed, right? Otherwise, you don't know how you're going to derive the values, the values of internal variables from external variables. So after you have rewritten the path condition in terms of external variables, then you basically just solve the constraint, right? You just assign different values to the external variables, and then